In this lecture, we are going to cover the second algorithm, that is for graph traversal, which is breadth first search, or BFS in short. In BFS, we try to explore nodes layer by layer. We start at a source node and then we visit the all immediate neighbors before we move to the next level of neighbors. I'll try to explain this with an example. For example, in a pond, you throw a stone from the top and you see that there are ripples. Okay, so here what happens is that we can see that the water, it is flowing in all the directions at the same speed. Okay, so similarly, if we can consider that there are nodes at each, there is node at every point, then the water, it is flowing in all the directions at the same time. Okay, instead of going in one direction, then coming back, then going in another direction, it doesn't go like that, right? It goes in all the direction with the same speed, with the same breadth, you can say. So what happens is that how we perform BFS. For performing BFS algorithm, we first pick a starting node and then we mark it as visited. Then we put this starting node into an empty queue, and while the queue doesn't get empty, we follow the procedure in which we first pull out the node from the front of the queue. Then we look at all the neighbors of this front node, and if the neighbor is not visited, then we mark that neighbor as visited and then we push it into the queue. Here we will try to see the BFS algorithm in action. So we will first select our starting point, which is A. Okay, so here we have the visited set in which we will keep track of all the different nodes that we have visited, and the queue is going to help us for the traversal. Firstly, in the empty queue, we are going to insert our starting point, which is A. Okay, so we have inserted A into the queue and we have marked it as visited first. Okay, so now our queue is not empty. While this queue gets empty, we are going to perform those three steps, which is first get the element out from the queue, and then second is look for all the neighbors of the front node. The third step, if any node is not visited for the front node, if any neighbor node is not visited for the front node, then we are going to mark that node as visited and push that into the queue. So we are going to first, this is the front node A, so we are going to take it out. So red means it is going to be taken out and green meant it was pushed. So it was pushed earlier. Now we take it out since it is the front node. And what we will do, we will look for all the neighbors of this node. So all the neighbors of node are B, C and D. Okay, so in B, D, C, all the three nodes, they are not visited yet. Therefore, we will mark them as visited and we are going to insert them into queue. So we will mark them visited by adding them into the visited set. So B, D and C, they are going to be inserted into the visited set and they will also be visited, they will also be inserted in the queue, and A is already taken out since we have to first take out the node. Now what is going to happen? This algorithm will continue on, and now the front node is actually B. So we are going to take B out. So it will become DC, the queue is DC and B is taken out. For B, we are going to look for its neighbors which are not visited. So E and F, they are not visited. So we are going to put E and F in the visited set and we are also going to push them in the queue. So E and F are going to be pushed into the queue and they are going to be added to the visited set. Now we have D as the front node. Okay, so D is going to be taken out. So it becomes CEF now. The queue is CEF. And for D, the neighbors are G and H, and they both are not visited yet. So we are going to add G and H to the visited set as well as to the queue. Okay. Now in the new queue, we have C as the front node. Okay, so we have to take C out of this queue. Now for C, we are going to look at its neighbor, and since all the neighbor of C and G is the only neighbor which is visited, so all the neighbor for C are visited, therefore we cannot mark any of its neighbor as visited. We will just move on to the next node. So we will move to E in the queue. After removing C, we move to the E. Similarly for E, there are also no unvisited neighbors, so we will move to the next one. Now for F, we can see that there are two unvisited neighbors which are I and J. Okay, so both are unvisited. So we will remove F from this queue and then we will add I and J to the visited set and the queue. So I and J are added. Now the front for this new queue is G. So if I look at G, here also I have one unvisited neighbor which is K. So we will first remove G and then we will add K to the visited set and the queue. Now the new front is H. So we are going to remove H from the queue, and since H does not have any unvisited neighbor, we are going to move the next one which is I. I also does not have unvisited neighbor, so we are going to move to J. J does not have any unvisited neighbor. It has a neighbor which is K, but it is already visited. So we will move to the next one, which is K. K does not have any neighbor. Therefore, we will move on, and now the queue is finally empty. So we stop over here. And here we have the list of all the neighbors, or sorry, all the nodes that we have visited using the BFS graph traversal algorithm. So this is the simple code we use for BFS. Here in Python, we are using the collection DQ, which is a built-in queue data structure. So what happened is that initially we are taking an visited set to keep track of all the nodes that we have visited. And the queue, it is a collections.dq. It takes argument as the initial queue elements, and initial queue element is only the start node, since we are marking it as visited, and then we are also editing it into the queue. While there is queue, meaning while there are one or more elements in the queue, what we are going to do, we are going to take the front element from the queue out. So the leftmost element is the front element. We are going to take it out, and then we are printing it, and then we are checking for all the neighbors of this front node. Okay, so for this front node, if the neighbor is not in the visited set, meaning that the neighbor is not visited yet, then what we are going to do, we are going to add it into the visited set and mark it as visited, and then we are going to push it into the queue. The key characteristics of BFS algorithm is, sorry, this is not DFS, it is BFS. So it uses a queue data structure to keep track of the visited nodes. Okay, that helps us in traversal. The queue data structure helps us in the traversal. The time complexity is big O of V plus E, where V is the vertices and E is the edges. The space complexity of this algorithm is big O of V, and that is for storing all the nodes in the queue, and also we are using the visited set for storing the visited nodes. Okay, and the common use cases of this algorithm are shortest path algorithm. We can use it to find the shortest path between two different nodes in case there are multiple path that goes from node A to node B. Okay, it can also be helpful in social networking platform. For example, finding mutual friends. Here it can be used friends which are at the degree of 1 from two from me and my friend. If they are at a separation degree of 1, then they are going to be mutual friends. And it can also be helpful in broadcasting, so sending information across a network to reach all the nodes quickly. All the connected nodes to a node, it can be broadcasted to that node. For example, I'm broadcasting to all my followers, then my followers can be represented as different node, and I can be represented as a node, and we are connected by directly one edge, right? So this was about BFS.